Hi friends, welcome back. In the previous video of design of a event detector, we went through the circuit design of an event detector for two scenarios where the data input to the event detector was asynchronous to its clock domain or it was synchronous to its clock domain. Now in this video we are going to write the HDL code of the both scenarios of the event detector and we are going to synthesize and simulate. So let's get started. So this is the HDL code of event detector when the data in is asynchronous. So we have the three inputs, clock, reset and data in, and one output which is basically generating a one clock cycle pulse whenever there is a rising or falling edge of the data in. So if you see here, we have the data in registered through the D flip-flop. So whenever there is a reset, the D flip-flop will get reset, otherwise the D flip-flop will sample the data in value. Then we have the XOR operation between the data in and the registered value of data in, which is nothing but the output of the D flip-flop. Then we are basically qualifying these two signals with using the XOR operations, and the output of the XOR operation is nothing but our event pulse. So let's synthesize this design. To synthesize the design, let's select the 𝐂𝐲 synthesis tool and enable the show diagram after run. Save the design and give a run. So this is the circuit diagram realized using the 𝐂𝐲 synthesis tool. So if you see here, we have the D flip-flop, the data in will get registered here, and then the registered data in and the data in will go through the XOR operations and we will have the event out. So this is pretty similar to what we have discussed in our event detector circuit design. So this was our event detector and this is similar to what we have seen in 𝐂𝐲 synthesized diagram. So now let's simulate this design. I have written the test bench, Verilog test bench to simulate this event detector design. So we will go through it. We have the clock, reset and data in input signals. We have the event out output signals. This is our DUT instantiation. Then we have a 10 nanosecond clock. Then we are driving the DUT. So initially we are actually resetting the design and asserting the reset and then deasserting the reset, and then we are randomly driving the input data in signal, and after 100 nanosecond we are finishing the simulation. And we have the initial block to dump the signals into waveform window. So now select the simulation tool and the Revera Pro simulation tool. Check the open EP wave after run and run it. So this is our waveform. So if you can see here, whenever the data in is transitioning from 0 to high, we have a clock pulse of 1 clock cycle. So if you see here in the waveforms, whenever the data in is transitioning from low to high, there is a 1 clock cycle pulse generated at the event detector output. Similarly, whenever there is a high to low transition at data in signal, we again have a 1 clock cycle pulse generated. Now let's synthesize and simulate the synchronized event detector, where we are actually synchronizing the data in input signal in our clock 1 domain, and then we are passing that signal to the event detector, and the event detector is then generating the event pulse. So here if you see, we have the three inputs and one event output signal, and here we are basically synchronizing our input signal. So we have incorporated 2D flip-flop synchronizer on reset. The flip-flop will get reset, otherwise the flip-flop 1 will get the data input value and the flip-flop 2 will get the flip-flop 1 output value. This is nothing but a 2D flip-flop synchronizer. Now the synchronized data in value, we are going to register the synchronized data in value using the D flip-flop, and then using the synchronized data in value output from the D flip-flop and the synchronized value coming from the 2D flip-flop synchronizer. We are basically qualifying these two signals through the XOR operations, and then the output of the XOR operation is nothing but our event out. So now let's synthesize this design. So if you see here, this is our data in. Data in will pass first through first flip-flop, then it will go to second flip-flop, and this is nothing but our synchronized value, data in value. Then the synchronized data in value we are registering using this D flip-flop register, and the output of this D flip-flop register and the synchronized data in value will be going to the XOR gate, and we have the finally event out signal. So this is pretty similar to what we have seen in our circuit design with the synchronized data in input. Now let's simulate the design. So I have written the test bench. We have these three inputs. This is our output signal. This we have our duty instantiation. Then we have our clock generated, 10 nanosecond clock generated. We are going to initialize the design, asserting and deasserting the reset signal, and then we are going to drive the data in signal. And we have this code to dump the signals into waveform window. Now let's select the Riveria simulation tool, enable the open EPFF after run, and give error. So if you see here, the data in was transitioning at this clock edge from low to high. So whenever the data in transitions from low to high, the data has to pass first through the 2D flip-flop synchronizer, and then it will go to the event detector. So after the 2 clock cycles, the data in the synchronous data in will go to the D flip-flop register. Here it will get registered, and the data in synchronized value will have the XOR operations, and during this clock cycle, actually for this clock period, we will get the pulse. So this pulse will basically get shifted by 2 clock cycles if we introduce the 2D flip-flop synchronized in our data in path. Similarly, whenever there is a transition from high to low, after 2 clock cycles, we again see a pulse generated here. So the pulse basically gets shifted by 2 clock cycles when we introduce the 2D flip-flop synchronizer. But the advantage of 2D flip-flop synchronizer is our data in which is coming from some unknown clock domains will get synchronized within our event detector domain, and then we will get a clean event out signal that will not be glitchy. That will be a perfect 1 clock cycle pulse. So hope this is clear to you. Friends, I have a question for you. So this event detector is basically detecting a 1 clock cycle pulse, or basically it is generating a 1 clock cycle pulse at every rising and falling edge of the data in input. So if we want to generate a pulse only during the rising edge of the data in and not during the falling edge of the data in, how we can modify this circuit design? Similarly, if we only want a clock pulse generated during the falling edge of the data in, how we can modify this circuit design? Please write down in the comment section if you know the answer. Otherwise, I will cover in some of the next video. Thank you very much. If you liked the content, please hit the like button. Also, please do subscribe this channel and enable the notification so you will get notified whenever I upload a new video. Thank you very much.